I would like to thank uh, all the collaborators that have been involved and are involved in this project of studying Icelandic glaciers. This is a close collaboration between the Veðurstofa, Jarðvísindastofnun, Landmælingar, and with also international colleagues. And I've wrapped up this presentation. So to begin with, I would like to talk about glacier mass balance. Glacier mass balance in a simplified version is simply the budget that the glacier has. So how much it accumulates in one season versus how much it melts. If it gains, for example, 8 meters in the winter and then it melts 5, that means that the glacier would have gained mass. The opposite, if it melts more than it gains, then it's gradually losing mass. Um, so this in 2014, this was defined as, well, they came up with a number of essential climate variables, and this was one of them. There's actually quite a lot of them, and it's quite interesting to read about that. Actually, now this year, they have defined glacier mass balance as one of the 7 headline indicators for global climate monitoring. So together with temperature or sea level rise, this is one of the main headline indicators of how the climate is progressing. So glaciers are in a way a thermometer to check how the climate is evolving, and they are really good at filtering noise on the short-term weather patterns, for example, and they reconstruct much better the long-term climate variability, and that's why it's important to monitor them. There was a study done last year by Guðfinna Aðalgeirsdóttir and a lot of colleagues that summarized the status of glacier mass balance in Iceland. This is the mass balance record of Vatnajökull, Langjökull, and Hofsjökull since the beginning of the observations in the late 80s. Oddur Sigurðsson started the campaigns in Hofsjökull, and Helgi Björnsson started in early 90s in Vatnajökull. And you could see how in early 2000s, the net annual mass balance was negative always. So there's always more more melt in the summer than gain in the winter. And these measurements are done every year, every season, in fact. In situ, they go to the glaciers and they drill in the spring to measure how much snow there is, and then they revisit them in the fall to measure how much it melts. And with this, they are collecting this time series. For us in particular, we are looking at another issue here, and this is when spatial information is quite important. We can, instead of measuring every year, we could calculate an average mass balance between a number of years if we have digital elevation models. So this is a clear example of it. If, for example, we have a digital elevation model from 2013 from lidar, we have another one from 2020. They look very similar, but this is not the same model. And you can actually compare them, calculate the difference in elevation, and this creates a map like the one I show here. And in blue, you can see actually some slight gain, and in red, you see all the loss of elevation. And with this map, you can actually calculate a volume. And this volume, it's giving you an average of the mass balance over this 7-year period. So then you can calculate, instead of this point-wise measurement, you could have a line showing the average in this time period. And this is quite important. In fact, it can be more accurate than the point-wise measurements that they do annually. So this is really useful for complementing the point-wise measurements, but it also covers really large areas if you have big data sets and large set of elevation models. So in Iceland, we've been creating and we've been compiling and processing elevation models. And this is all using open data, or mostly open data. And I'm just going to show quickly the main sources of elevation data that we've been using. First of all, we're using aerial photographs. These are stored at the archives at Landmælingar, and they are being scanned. So you could see, for example, images that reach as early as the 40s, 1945 to be precise. This is Eyjafjallajökull. other data sets are available from abroad. For example, in the 80s or late 70s to early 80s, there were big campaigns from the Americans. These were, at the time, they were spy campaigns to monitor the whole world, but then they became declassified and they covered from satellite, taking photographs. They cover most of the world, also in stereo. So this is also another source to create elevation. Nowadays, we have a lot more variety of sensors and methods to create elevation in more detail. For example, we have lidar that creates really, really fine and precise point clouds. This is a point cloud in Snæfell, collected by lidar in 2012. And we have a lot of satellite submitter stereo images that have the same principle as the aerial photographs. They collect two images and you get the perspective and you can create a 3D model from that with a submitter pixel. And then this covers huge areas and you can create also elevation. Like the one I showed for Hofsjökull, this was coming from this French satellite called Pléiades. And a bit of an overview of the mapping done in Iceland with lidar. This was a big effort done by the colleagues, especially led by Thomas Johannesson at Veðurstofa. Since 2008 until 2013, they mapped all the glaciers of Iceland. And this was intended for this specific purpose, just to create a benchmark dataset to compare elevation before 2010, after 2010, with the lidar, which is a really accurate map. This is an overview of the maps, and it's also important to highlight that this is not a trivial issue. For example, if you want to cover Vatnajökull with lidar, you need actually quite a lot of effort on surveying in many, many dates. Each day you can maybe cover 100 or 200 square kilometers out of the 9,000 square kilometers of Vatnajökull. So they did it over the course of 2 years. Like I mentioned, we also have quite some efforts of collecting elevation data of glaciers through our French collaborators, and in particular, there is this French satellite named Pléiades that it was launched in 2013, and we've been testing it in Iceland. This is through our colleague Etienne Berthier, who's working in Toulouse, and he has a lot more access to this satellite than foreign institutions. So we are working in a collaboration with him, and we've mapped also almost all glaciers. This map is not updated, and we have also Hofsjökull, and this summer we are aiming to cover also Langjökull. For curiosity, this is the same satellite that it was used for the first 10 days of the eruption in Fagradalsfjall. So we collected 5 stereo acquisitions in Fagradalsfjall, making DEMs of the eruption and calculating volumes. So it is similar to what we do for glaciers, but for lavas. And of course, we have also ArcticDEM. ArcticDEM is an excellent data set that became publicly available in 2015, I think. They started collecting since 2008, but significant data was collected since 2012 until present. But there is the officially released data that was done by ArcticDEM stops in 2017. I know they are trying to push for more open data, but at the moment it hasn't been open. So this is done by the Polar Geospatial Center in Minnesota, and they have collected loads and loads of different parts of the country, and in fact they are doing this for the whole Arctic, also with very high resolution and level of detail. So this is another important source of spatial data. If we wrap up all this and make an overview, for example, for a single glacier, now we are looking a lot more into Hofsjökull as a test site to evaluate methods. We have a timeline like this. We have aerial photographs every 10 years, 15 years, up to 20 years. And then after 2000, we start to get more and more elevation data from satellites. We also have lidar surveys, 3 surveys in Hofsjökull, 2008, 2010, and 2013. So if you see this, you could see it as a stack of multiple elevations. And if you're looking at a single grid cell, for example, 5 by 5 meters, you would see that there are actually 10 up to 20 elevation points in a time span of 12 years. So now this becomes a problem of spatial and temporal data and how to handle it, because it has a lot of discontinuities. Maybe you have a small survey. I don't know if you can see this triangle here. This is from a lidar survey that covered this small portion in 2010. You don't have complete coverage at once. You have mostly just sparse surveys over time, but overall you have a lot of points. So we're trying to find methods to automatically interpret all this data that is discontinuous in time and in space. And for that, again, I'm going back to the French colleagues because they've been doing something similar also with another data set that became fully open in 2015, which is Aster. Aster has been collecting data since 2000, and this is very coarse resolution. It has 30 by 30 meters, the pixel size of the DEMs, so you don't get as much detail, but you have a lot of data over and over. So they are thinking already on this type of stacks of data and how to get useful information in glaciology with that data. So for one single pixel on a glacier, you could see it as a stack of elevation points. And then they've been coming up with methods, for example, to fit for each pixel a trend, a linear trend simply. And with that, they could come up with a consistent survey at a given date. For example, if you could fit a trend for each pixel, then you could interpolate and get the DEM from 2010. And this is what they've been doing, and they've been doing big picture studies, global or region-wide studies, and now they have come up with a global study using a more robust method. Instead of a linear trend, they're using something called Gaussian processes that just fit for every pixel something that is not linear, and it covers annual variability and seasonal variability of elevation. So you are actually capturing all these variations that you have in a glacier, all these elevation changes that are a function of annual changes and seasonal changes and multi-annual changes. And this is coming now to a paper that is now accepted and it will be published very soon, containing the big picture of all the glacier changes since 2000 to 2020 based on Aster. So we took this method and we did the same for our dataset, which is not as dense as Aster, but much more detailed. So we wanted to see what you can do with that. And like I said, you can then interpolate and create continuous maps. So we could create DEMs every month since 2008 and calculate the difference between them. So you could see with that, this figure showing the changes, monthly changes. And this shows even like breathing of the satellite, this type of like seasonal variability, how it just thickens during the winter and it lowers more during the summer, and then the long-term variability. So this creates a stack that you can then also slice, and you can calculate a model of a given date. For example, we could also calculate an elevation model of October 2008, October 2009, October 2010, and calculate the difference between all of them. So you end up with time series like the one I'm showing here. And this is reliable. You could see that some years have been much warmer. Then, for example, 2013 to 2014, it was quite cold winter in 2014. So you actually see this increasing of accumulation in the upper part of the glacier. Another way to look at this would be simply to look at a single point and to calculate all the elevation points that we have interpolated. Some of them are actual observations. So for example, at a certain point at the top of Hofsjökull, at the caldera, you would see this red dot showing the actual observations, and the blue line shows the interpolated data. And this fits actually quite well with glaciological interpretations of how a glacier should behave. You could see that the ablation area has a really linear decay in elevation, whereas the accumulation area has much more oscillations. And this is explained in glaciology, and you could say that the lower part of a glacier is showing the long-term climate variability, whereas the upper part is showing more the short-term, which you can call almost like a weather variability, which has much more fluctuations. So you could see that nicely in these figures. So we are using this as a way to calculate much more robust mass balance, and not only over a period of 7 years like I was showing before, but annually. So we are now, for example, like trying to calculate annual mass balance compared with in situ mass balance. We are still doing fine tuning of this because there are other factors affecting the comparison. This is not an apples to apples comparison. We need to think on the density on the snow, on other processes affecting this process. But overall, we are quite happy to see that this is working for calculating really finely elevation changes of glaciers. And just a few takeaway messages of this. For this to have happened, we needed to have Aster openly available, so the French colleagues would be able to explore all these methods of stacking of elevation and to explore all these complicated and like processing of heavy data sets and fitting trends into them and so on. We needed to have the ArcticDEM also. So ArcticDEM has been a great help for this, and the lidar. This is all open data. It's of course not all the data has been open, and Pléiades in particular is a French satellite. It's split between the French Space Agency and Airbus, which is completely commercial. But our French colleagues are, in fact, that's their fight. They are trying to open all the data collected of Pléiades for glaciers. They've already succeeded with Spot 5. Spot 5 was running until 2015, and now they have agreed that this data will be open, but Pléiades is still not fully open, but we get access to it through research. And we can see also that currently the best methods for mapping these large-scale glaciers like Vatnajökull relies at the moment on satellite stereo images and lidar if possible. It's also important to highlight that the lidar surveys that happened in Iceland they are now quite old. I think the latest one happened in 2013. So of course, other lidar surveys at this stage would be also very welcome as a way to further calibrate and evaluate all these methods. But at the moment also we are relying on satellite stereo images, which are of great use. And then on the research part of this project, we've seen that now we are coming with methods of large data set interpretation and processing using Gaussian processes. So we are fitting stacks of elevation and calculating trends per each cell and creating all these dense time series of homogeneous elevation change in glaciers. So this was my presentation. This is actually in the background. This is Hofsjökull. This is the last images that we acquired from Pléiades last fall in 2020, just when the first snow started to arrive, and you could see here the drumlins and the moraines with a false color infrared image. So thank you very much.